Hey everyone, like Dino said, I'm going to talk about IoT data architectures, and particularly the trickier IoT data architectures, the ones that you can't just do in the cloud, you actually have to do some at the edge as well. So we're going to explore what it means to put these things together and have the data flowing through. So I'm going to take it in two parts. First part's going to be some general trends I see that are influencing industrial IoT. So like I said, this is going to be the trickier of IoT use cases, the industrial use cases, as opposed to consumer IoT. So as much as I'd love to talk about smartwatches and smart homes and things like that, that kind of stuff, generally you can do all in the cloud. Here are the trickier ones that involve big machinery, where the data architectures get a little harder to do. So talk about the trends, and then I'll get into some ideas around how to design data architectures that make those use cases possible. Obligatory bio slide, you guys heard it already. I'm at MapR. I went to school. So starting out with the trends, and for starters, I just want to do a level set on industries and use cases that I see quite a bit of and kind of influence this thinking. So going counterclockwise, so there's kind of this category of use cases that spans from energy, mining, agriculture, and these, like in real life, these aren't really that related. Like you've got oil wells, and then you've got gold mines and farms. But when it comes to data architectures and IoT, they're actually very closely related in that there's machinery running at all of these different places. There's something getting produced, so people are very worried about being more productive, getting higher yield, finding more oil, having better crops, and they're usually far flung. So they aren't abutting major cities where they're going to have a fiber optic connection plugged in. There's generally little to no internet connectivity going to these places, which makes doing interesting applications pretty tricky. Next, moving on to medical devices. There's a lot of use cases here. Some of these you'll read in the news, from doctors are going obsolete because AI is taking over. It's a little hyperbole, but there is really interesting stuff going on in this space around training artificial intelligence algorithms to look at radiology images like MRIs, CT scan, and at least suggest to doctors kind of where they should be looking on those scans. So lots of exciting things for just patient treatment over time. Manufacturing, it's kind of similar to the energy, mining, and agriculture, except bigger spaces, more machinery, and maybe a little bit more connectivity. But it's same kind of things people are trying to do with it. People want to get more productive, have higher quality, and have stuff fail less often, because for a lot of these things, when you're working with big machinery, stuff gets expensive when it fails, and you're quite a bit less productive when you can't actually use your machines. So there's enormous value in predicting when things are going to fail so that you can maintain them and keep them up and running. And last is this kind of catch-all category I call remote operations. And this is the category for those of you that say, I don't have a factory, I don't have an oil well, what does any of this have to do with me? And one example I'll give you for this one is I'm working with a major financial services company who, unsurprisingly, is extremely concerned with cybersecurity. So for them, they have a need to do network level analysis, so collecting lots of network traffic from remote locations. So these are branch locations, remote data centers, places like that. And their problem, the ratio is the same of data collected to internet connectivity, because they're collecting 10 gigabits per second worth of traffic from a lot of these very remote locations. So even with all the fiber optic cable they have buried, it's not worth sending 10 gigabits worth of traffic to some central site to figure out whether they're under attack or not. So by using some of the same techniques that you'll see in these other industries to do localized processing and intelligence, they're able to have a more secure network. Beyond that, anyone that has video has a use case for doing local processing of that video. So that's kind of my catch-all category. And a lot of people kind of have ideas for use cases and want to do more of this in their organizations, and they just have a problem of ultimately somebody's going to write the check for it, wants to know where the ROI is. So I've got this slide here just as a means to say, if you're trying to convince people in your organization to invest in this, there is quantification in terms of ROI for these things. So the first one is just everybody's doing it, so it's the FOMO piece of it, but going down, reduce supply chain forecasting by 50%, lost sales by 65%. This stuff is specific to manufacturing, but the same sort of research exists in all of the different industries. And manufacturers are improving semiconductor yields by up to 30%. Now, when I first read this one, the 30%, it was like, oh, 30%, that's kind of nice. But then you consider how hard it is to make any sort of improvement to semiconductor yields. Like, this is the kind of thing where people have 1-2% increases and they pat themselves on the back. So 30% is pretty impressive. So it kind of lends credibility to investing in this kind of technology. So now, just some other things that are making all of this possible. So one, I call it data scientists leaving the playground. So companies that are implementing these use cases are moving in kind of this continuum of data analysis to data science to what I call operationalization of AI. And what I mean by that is historically what they've had is analysts that collect historical data, slice and dice it, and build reports to try to make decisions for the company. And any of you that have ever done this know that that whole process of collecting to getting the right data to defending the data and having all the meetings means you spend 6 months to try to make a decision that might impact your business 6 months in the future. So this is definitely for long-term decision making. So as companies mature a little bit, start hiring data scientists, those data scientists start collecting that same data and building models on it, what you quickly move from is this backward-looking analytics to more forward-looking analytics, because these models they're used to make predictions. But now, basically, what you have is somebody that builds a model, that model's sitting on their laptop, and they can use it to do things like forecast what sales are going to look like next quarter. So you can make a lot of improvements on the things that you'd been doing kind of suboptimally before, but it's kind of short-term decision making in that you can influence your supply chain efficiency for next month or next quarter, but you're not doing too much in the moment. If you want to get improvements in the moment, you do this operationalization of AI, which basically says that you have those data scientists, they're building models, but instead of just looking at those models and trying to make decisions directly based on them, you take them and you put them into your operational systems and your operational data pipelines, and you start making predictions about certain pieces of data and certain objects as your business runs. So for example, it's this that allows you to build a model of what a tractor should operate like. So take all of the stimuli from the tractor, all of the sensors, and use that to build a model of what a healthy tractor looks like. That way, when you start getting signals that don't look like that, you can, in the moment, predict this tractor is about to fail, and you can take action. So that's the difference between using data science and models for short-term decision-making to doing things in the moment. And there's a lot more examples of this. Again, if we take manufacturing, there's lots and lots of things that are changing along this same continuum. So it's everything from manual assembly to semi-automated to robots everywhere, think Tesla factories. Supply chain, so your supply chain sucks, to it's a little bit better to actually doing automated ordering of things based on these predictions. And there's more and more of these kind of examples. So that's kind of the AI side of IoT trends. When it comes to data architectures, what's going on is a couple of things. So first, as more and more companies try to implement use cases that need to do things in real time, make decisions in real time, collect data in real time, show dashboards in real time, you have to build an architecture that's able to collect data in real time. And the protocol or the language of real time is publish, subscribe. So increasingly what you're seeing is sensors growing up speaking pub sub, and the different data architecture speaking pub sub, and just everything built around this kind of hub and spoke pub sub system at the edge. Next, what we're seeing is these modern computer vision algorithms are paving the way for what I've been calling video as the Uber sensor. So I'm working with several customers who have kind of had this realization that if you want to gain more visibility into your operations, there's a couple of ways you can go about it. One is you can place a lot of little sensors out there to do very specific things. So in the case of a field, you can place humidity sensors everywhere, or in the factory, there's vibration, temperature. You can place all these sensors everywhere and try to get all of that data in and make decisions based on it. Or you can just place a video camera somewhere where each pixel of that video is in fact a sensor, but you only had to put one thing in one place. And what's interesting about this is you can actually see more with a video frame than you can with, in some cases, thousands of sensors. So one example is a semiconductor, not a semiconductor, a PCB manufacturer, so printed circuit boards, the stuff that goes in all the electronics. Of course they have lots of sensors along their line, but they only tell them if their machinery is working. They didn't have any sensor that said, is the thing that machinery built defective or is it high quality? Which meant that they had to ship it to another facility, do a power on self-test, and only then would they realize if it was good or bad. And by then they'd already spent all the shipping money, and now they have to bin it and have all these processes. So what they did was they just put a video camera at the end of their production line that took pictures of all the PCBs as it went down, and then they spent a little bit of time collecting that data and marking which of those pictures were for defective PCBs, which ones were the good PCBs, and then they just turned on the algorithm so that as the boards went down the line, it would take a picture, and the algorithm would say, it's a good PCB, let it go. Bad PCB, a hand would come over, knock it off, and they'd keep the line going. That's one example. You see a lot of this in agriculture because fields are big. You can put a lot of sensors out there, or you can fly a drone overhead with a video camera on it and get even more level of detail if you just apply the right algorithms to it. So I think increasingly we'll see video being used as a surrogate or Uber sensor in these locations. But pair that with the fact that a lot of these use cases are being put in far-flung locations where they have either not a whole lot of internet bandwidth or it's unreliable. So a lot of times on oil platforms, they'll try to use satellite as a means to do internet connectivity or 3G, 4G. And when it's up and there's no clouds and things like that, it's probably got enough bandwidth to handle everything. But a cloud rolls over, now you have no connectivity. So you don't want to be in a situation where a cloud rolls over and that's just the time when your thing's about to fail. Or you're, in case of oil wells, we don't want anything to dump into the ocean. So now you've got these two competing things. So lots and lots more data getting collected at a higher frequency, but crappy internet connections preventing you from doing anything useful with it. Luckily, our friend Gordon Moore and his law have made it such that the computing power that you can put at the edge and your ability to store data locally at the edge has gotten to the point where you can actually implement really interesting use cases in small form factors. So this is kind of the solution to collecting more and more data, can't send it across, you have to compute it locally, and this is the whole basis behind edge computing. So with all of that in mind, let me suggest some ways that I see that people are building architectures that solve this. Now first, just think about what it takes to put AI into a use case. One of the analyst reports came out that said 75% of the work it takes to build an AI use case is the data engineering. It's getting the right data from the right place into the right format so that you can finally use one of these new algorithms to get insight. And kind of reverse engineering what all it takes to implement one of these. Let's start from the right side with you have an AI use case. So an example of that is predicting remaining useful life for a piece of machinery. To do that, you need to have models running in production that's actively processing the new data that's getting generated for that particular piece of equipment. To have models running in production, you need to have a full process around data collection, feature extraction, model development, deployment, testing, all of that. And then to have that, you need to be able to reach into all the different places that the data might reside in, whether it's real time or batch. You need this system of record. It has to be secure because you want the right applications and the right people to access it, but not the wrong ones. Governed so that you can actually trust the data, and flexible enough for everyone that needs to help design this to actually be successful. So there's a lot that goes into it. So this is where all of the planning that comes into play when building these use cases. Not to undermine the AI piece. That piece is pretty hard too. So trend number one, edge-first processing. This one's evident from the diagram earlier of the bandwidth imbalance. So when it comes to edge-first processing, basically what we're talking about is taking the overall application logic that you're creating and distributing it among what you're going to deploy in the core. This could be in the cloud, it could be in a data center that you own, and taking another piece of it and running it close to where the data is being created to solve this bandwidth imbalance problem. And if you look at the first bullet, that's kind of the mantra of how these things successfully get developed, which is act locally, learn globally. So you want to act locally because you want to act before you're inhibited by the bandwidth or the internet connection that you have. But you want to learn globally because the actual AI and machine learning models that are going to make the most impact at the edge can't be developed using only the data that that particular edge has seen. The best models are created by the most data and the most variety of data that's been generated from everywhere. So what it means is you have to have this architecture where the edge is enabled to make local decisions, but also it feeds a continuous stream of data to the core so that the core can run the machine learning algorithms, build the models, and in turn ship those back to the edge, and do this in a continuous fashion so you're always learning, you're always improving. So double clicking on that a little bit, what does it take to actually build one of these architectures? So we see here, the left piece of it shows what you're running at the edge, the middle and right piece is what you're running at the core. So at the edge, obviously you need to run, so one way of looking at a machine learning model is it's an application. It's an application that takes data in and a classification or a decision out. It's an application, so you have to run those applications at the edge. You need something to handle all of the data, so you need some streaming, publish, subscribe, broker, bus, however we want to think about it. And then you probably need some storage. So if it's time series data, like sensors that are emitting timestamp, comma, some sensor reading, a time series database makes sense. We see OpenTSDB, just an open source one, deployed quite a bit. If it's video data, image data, then it's probably more likely that you're just going to want raw file system storage. Somewhere in between, you might want a NoSQL database, but you need some storage at the edge, if nothing else than to act, as a buffer for the data that hasn't yet made it into the core. But more importantly, what the application at the edge is supposed to be doing is summarizing and filtering data before it gets to the core so that you can make the most use of that connectivity. So to the extent that it can aggregate data before it gets to the core, it will, because that really cuts down on the size. And the rest of it's about getting rid of all of the uninteresting data so that it just sends the interesting pieces. So when it comes to sensor readings, the easiest stuff is if nothing's happening, don't send the data. You might want to hold on to it locally, but don't waste internet connection on stuff that you know is not going to be useful for model building. later on. But send what is, because again, you have to keep improving things. So then we get to the core. So typically the connection between the edge and the core is going to be another publish subscribe bus, because you want that connection to be real time and always be collecting data at the core. So that's where you start with streams. And then again, you can use files and NoSQL databases depending on your data type and what your goals are. But of course, you're going to need to process the data, get it in the right format. So just naming some open source projects that you might use for this. Apache Spark is the one that I see most often used for the ETL processing or stream processing at the core. You still, even though you're building these models, people are still going to want to see reports on what's going on right now, how's my operation doing. As long as they're executives, they're going to want to see reports. So you're going to need to query that data. There's an open source tool out there called Apache Drill that does a really good job of this on a distributed platform. But then the most important thing is actually building those models. And there's, just given where we are with machine learning and AI today, there's a lot of tools out there used to build these models. So I named a few. Spark does a little bit of it. Many of you've heard of TensorFlow that came out of Google, MXNet that came out of Amazon. These all do a pretty good job of taking data in and spitting models out. And then once you train that model, then there's this reverse arrow for sending those models back to the edge. And again, you do this continuously. So taking this one step further and applying it to one of these use cases, let's think about a farm that has a drone taking video, and your goal is to figure out and optimize, so figure out which parts of your farm, so usually you divide it up into quadrants or segments, and you want to optimize the yield of each one, which means you have to understand how healthy the plants are in each one of those areas, and if they aren't healthy, kind of what they need. So we've got this drone, we've got the video. The easiest way to summarize video data is to convert it into metadata. So the goal would be to have a image classification algorithm running somewhere local to that drone. Maybe it's on the drone, maybe it's on a truck nearby, wirelessly connected, varies. But it takes that video in, and it has to know from looking at a particular frame whether, and it's going to be a lot more complex than this, but for simplicity's sake, let's say it can tell whether a plant is healthy, needs water, needs fertilizer, or there's a rabbit eating it or something like that. That is the metadata stream that then gets fed into the core along with filtered images. So a lot of times the way these image detection algorithms work is you feed it a frame and it'll feed you a classification and a score for how strongly it feels about that classification. So if it's 100%, if it 100% says this plant's healthy, you can probably be safe and say, I believe it. But if it says 50%, it's like you can probably make a decision based on it, but that is now an interesting image that you might want to feed back to the core so that you can refine your learning and be more sure about that classification moving forward. But you see from this, you've filtered down the data by converting it to metadata and filtering out those images. You've probably filtered it by a factor of 100 and made better use of that. And you can actually, all along you've been making local decisions at the edge with the models that you have on site. Now, part of the tricky thing about this is there's a lot of even consumer technology right now for doing image detection. Like you can upload a photo to Amazon or Google and they'll send you back the things that they see in that photo. But the built-in models will help you do things like tell the difference between a person and a plant, but not the difference between a plant and a plant that needs water. For that, you have to train a new model, which means feeding more data into one of these frameworks and spitting something out. So kind of tricky to build, but if you architect something like this, you can achieve it. We're seeing more and more of that happen. So once you get data back into your central site, there's a lot of decisions to be made about what's the best way to store it, what's the best way to make it available for applications, and what's the best way to actually build out those applications. So one of the other trends that I'm seeing in this industry, and this isn't really specific to IoT, but it helps, is this concept of stream of record. Now, stream of record is the concept that you take your publish subscribe system and use the historical buffer in that system to be your system of record for the data going through it. So this is as opposed to feeding data through your publish subscribe system into a database like an Oracle or something like that and making that your system of record. And then pulling data out of that database and pulling it into whatever other system that you might want to do analytics in. So this is based on the fact that more and more publish subscribe systems like Kafka, and we have one at MapR, actually holds on to data after delivering it. So it enables you to have this historical buffer. But the benefit of this is huge because every time a new use case comes, what you'll find is those new use cases are going to require a different type of analysis of that data or a different type of storage of the data. So it could be that you need a column optimized database like Vertica to analyze that data. So you need a way to hydrate a Vertica system and do something useful with it. It could be that you need to represent your data into a graph database or a time series database in order to do a different kind of analytic. And contrasting pulling data out of one operational database system and ETLing it into these other ones, it usually takes weeks because you need to kind of plan it out. You have to make sure that you don't pull out of the database at a time, that you have something else going. DBAs always yell at you for touching the database a little too heavily at the wrong time. So if you go with this stream of record, basically what it says is all you have to do is build a little app that sits right here every time you have a new use case that reads the infinite history of the data that's gone through and fills up a data store, whether it's a columnar database, row-oriented database, a JSON database, a graph database, files, whatever it happens to be. You can just change this logic, reread from here, populate these, and if they work, great, you can build your app on top of it. And the best part is if they work, because this is pub sub, everything is real time, the database is always going to be kept up to date because you first read the historical information, but as long as you don't turn off that app, the next reading that comes through is going to get sent into this data store, the next one that comes through. So now you have materialized views that are always updating live. And if they don't work, you get rid of it, you decommission it, put something else up that works, and then you get use out of it. So one of the companies that adopted this architecture said that it made their development agility go up by 3x because they went from going weeks from I need to get this data in this format to do my use case to I can just do it over lunch. There's also compliance benefits as well, but I won't get into that for time. So that was the last of my material. I have just a couple of recommendations on books to read if you're into this sort of thing. The one on the left covers a lot of the architectural considerations for doing distributed data streaming and analytics. The other one is just a general streaming architecture book that would get more into the stream of record. So I'd recommend, they're free if you go to mapr.com. Recommend getting into those if you want to know more. But that's, look at that.
Good job.
Thank you.